So let me just quickly go through then. So what we have done since the beginning. So we are assuming this x follow f theta x. This is the Fisher's definition of Fisher information. Ix theta is expected value of del theta log f theta x whole square, or you can define it as a minus expectation del theta 2 log f theta x. So when we did this Poisson distribution, we use this definition to calculate Ix theta. But if you use this definition also, you will get the same answer. You're supposed to get the same answer. If you're not getting the same answer, probably you're making some calculation mistake. Then the first example we took that x follow Poisson lambda. So the f of lambda, the PMF is e to the power minus lambda lambda to the power x factorial. We took the log of the PMF and then we differentiate with respect to lambda, and then we differentiate twice with respect to lambda. That gives us minus x over lambda square. And then when we take the expectation, we get this Fisher's information for Poisson distribution. Then we considered x1, x2, xn IID samples coming from Poisson distribution with parameter lambda. Then the Fisher's what is the Fisher information of x tilde? So we have this result from the last lecture where it says that if x1, x2, xn are coming from IID with f theta x, then the Fisher information of x tilde is n times I of x1 theta. So we used this result to say that for Poisson distribution, Fisher information for x tilde is n by lambda. Then we considered the third example, x1, x2, xn following IID Poisson lambda, tx tilde equal to t is summation xi is a statistic for lambda. Then question is, what is the Fisher information of t? Turns out t itself follow Poisson in lambda. And then question is, what it lambda follows? What is the value of, what is the form of it lambda? So we took the PMF of it lambda, PMF of the Poisson in lambda, which is e to the power minus n lambda to the power t by t factorial. We took the log of that, then differentiate with respect to lambda. Then we differentiate with respect to, again, the second differentiation. We take the expectation and we found it lambda is n by lambda. And we realized that, okay, Ix tilde lambda is equal to it of lambda is n by lambda. So that means that whatever information I have in my x1, x2, xn, the t of summation xi contains the same information. Ix tilde lambda and it lambda is exactly same, that is n by lambda. So we can call it t is a sufficient statistic for lambda. T may not be the estimator for lambda, but we can use t to do some further calculation. Now, when we are saying,
excuse me, sir.
Yeah.
Sir, like when you are calculating the sufficient, like this information for n lambda, like t is in the example 3 which you showed, here t follows n lambda. So why can't we replace just lambda with n lambda, because it's Poisson, and like why can't we relate example 1 and 3? Like I was thinking it would come out to be 1 by n lambda.
Yeah, intuitively that is what we can think of, but there is a scaling effect, and that scaling effect working here, because this is actually, you can write it as a t log n plus t log lambda. Then when you're differentiating with respect to lambda, it will be 0. And so this part is coming out as a t by lambda. And hence we have this guy here. So when actually calculating, turning out that it is not 1 by lambda, it is n by lambda. When we are doing the actual calculation. So sometimes our intuition fails, and this is one example where intuition actually fails. Correct?
Yes, sir.
So this is, so you have to actually do the calculation and then only you will get the answer. You understand what I'm saying?
Yes, sir. And yes, sir, I understood that. And sir, does that mean every time that we cannot just take it like that? We have to, whenever it's asked for a sufficient statistics, we have to calculate it separately, irrespective of whether we have
It is
calculated
better,
it previously
see,
or
if it is better to do the mathematical, I mean, do any, come up with solution with more mathematical rigor. If you know this path is little lengthier, let's take that lengthier route, because intuition might actually lead you to little wrong conclusion. Okay. So that's why I took the little longer route to actually derive and figure it out. Okay.
Okay, sir.
Yeah. So expectation of t is, we know, n lambda, and variance of t also we know n lambda, right? We can use this as typically what we do. We say that, okay, you take t by n as lambda, and then what will be the variance of t by n? Variance of t by n will be 1 by n square, variance of t, and variance of t is n lambda by n square, and hence we come up with m lambda by n. And what is t by n? T by n is simply x bar, right? The problem is we do not know exact distribution of x bar. We do not know exact distribution of x bar. So it's difficult. The question is, what is the, can I say something about x bar lambda? So in this case, the problem is I do know that it of lambda is n by lambda. The question is, what is the, and turns out x bar is my unbiased estimator, but I don't know exact sampling distribution of x bar. Therefore, I cannot directly compute the variance of the Fisher's information of x bar. Any idea how can we solve this problem?
So using Monte Carlo estimate of the
Monte Carlo is not a, Monte Carlo will not be very much helpful here.
to calculate the expected value.
No, I mean, mathematically, when you approach it, there is a, so here, effectively the one I'm trying to argue here is that if you know that T is, if basically what I'm trying to say that I don't know how to solve this problem, to be honest. Okay. So if I cannot solve this problem directly, can I solve it indirectly? Now I'm motivating you to another direction. So T is, if we can somehow show that T is sufficient statistic, and some one-to-one function, I already actually used G, so I don't want to use G. Let me use a H. Some H of T is also sufficient statistic. Because I already have shown T is sufficient. If I somehow also can show that if T is sufficient, then H of T is also sufficient statistics. If say H is a one-to-one function or something like, if I can develop some result like this, then I'm done. I don't have to actually derive this separately and check. All I have to show that, okay, I just only showed that T is sufficient, okay, and X bar is a function of T. If I can develop some generic result, a theorem that T is sufficient statistics implies some function of T is will also sufficient, then I'm done. Then I'll say that, okay, X bar is also sufficient. I'm going, so that is my end goal, that I know somehow if I can find one statistic, all I have to, so basically then all I have to do, I have to find one sufficient statistic, and then whatever estimator I'm going to use, I will just use that as a function of that sufficient statistic, and I'll be confident that yes, that estimator will also contain all the information that I have in the data set. Okay, so this is what this is a result or we want to figure out. I don't know, at this moment we don't know whether this kind of result exists or not. Okay, but do you get the motivation? So now I am going to take a detour of the way. So now I'm actually moving to from Nitish Mukhopadhyay's book to Kasselberger on statistical inference. The way most of the textbook actually define the sufficient statistics, and this is I'm taking from Kasselberger. The definition that, and this is exact definition of Fisher. It says that a statistic P of X tilde is sufficient statistic for theta if the conditional distribution of the sample X tilde given the value of tx tilde, given the value of tx tilde does not depend on theta, does not depend on theta. Now, what does it mean? I mean, first time if you read this definition, it feels very weird, to be honest, that what exactly on earth, how somebody can come up with this kind of definition. So what he's saying that the conditional distribution of the sample X, so you have X1 to Xn, this is my X tilde, from f theta X, IIT, and you have a statistic Tx tilde, some statistic, then what he's suggesting, the definition is suggesting that P theta X tilde equal to small x tilde, given T of x tilde equal to T of small x tilde, this conditional distribution will be phi of theta. So that is what it will be, completely like something like this, h of completely x tilde. Like it will be completely, it will not, it will be a function of only sample. And so let me just actually write it in this way. This h of x tilde is only function of x tilde, that is data, and completely free of theta. If that happens, then T x tilde is sufficient statistic. So that is what Fisher's definition is of sufficient statistic. Now, what is the motivation of that? The motivation, I mean, it took quite a bit for me, and I'll try to explain, and I don't know, I don't claim that, you know, it will be that easy to, and also it's bit of a, sometimes I feel very weird also, this definition. I never felt comfortable with this definition. It looks like it's fall from sky. So let me try to explain it. Sorry. Consider two experimenter, okay? Consider two experimenter. One is one observe, so experimenter 1 and experimenter 2. So they do exact same experiment, or maybe they are just two surveyors, just they go to the field and collect some survey samples, and they run the exact same set of questionnaires, or this kind of thing. And one person got observed. One person observed x equal to x tilde. Another person may have observed x tilde equal to x. Another person may have observed y tilde, x equal to y tilde. They're both observing the x tilde, but one got the x realization, another got a y realization. Two different realization. Now, if it is possible that t x tilde is very much equal to t y tilde, even if they have a separate realization, but they may end up in the same statistic. It's like one person is observing, say, one person is observing a sample of 1, 3, and 5. And if you take the average of this, the average will be 3. And another person is observing maybe, I don't know, 2, 3, and 4. And in this case also, the average will be 3. So two different realization. This is x tilde, small x tilde, and this is small y tilde. Just two different realization, but same statistic. With tx tilde comes 3 and ty tilde comes 3. So probability of x equal to small y, given that these two statistics will be exactly same, this probability this probability distribution, this will be a distribution probability distribution on a sample space where y tilde is such that tx tilde equal to ty tilde.
Sir, is it not x tilde over here?
Which one?
The line probability x is equals to y tilde. I think it should be x tilde equals to y tilde.
No, this is, I'm thinking from, I mean, yeah, you can take x tilde also. I'm just thinking from experimenter 2's perspective. You can write it in x tilde also. I'm just from experimenter 2's perspective, that experimenter has observed only y tilde. Suppose they are double blind. Okay. In that case, what I'm trying to say that for experimenter 2, given that if they're using the sufficient statistic, then this conditional distribution will be a probability distribution on this particular sample space or party. It's a, you can think of it as a partition on the entire sample space. which the partition is done based on this condition. Like for the different realization for which it gives the exact same statistic. You can think of, suppose your sample of size 3, x1, x2, x3, x1, x2, x3. Now you think of how many such partition is possible. All these partitions you consider, all those partitions consider. Now the partitions which are giving the same exact t, those partitions, that is as a one case. So that's how you can think of. And this probability distribution, you don't need any knowledge of theta to compute this probability distribution. It's just a certain partition of the sample space. You don't need to have any knowledge of theta, as long as tx tilde equal to ty tilde, if you can ensure that. But if they are not same, then you would of course require then there will be some overlapping of partitions. So suppose what I'm saying that if tx tilde not necessarily equal to ty tilde, then what happens is, suppose these are the partitions, and there could be a partition like this, and then could be partition like this, and then this guy will be double counted. Now where will be double counted, where it will not be double counted, for that counting process you will need some information about theta. But if you can make sure it is like this, that they're mutually exclusive. Suppose these sample, this is a x and this is a y, and if you apply on t, they will give you exact same answer. And this is another x and y, and if you apply t, they give a exact same answer, and they're mutually exclusive. Then essentially you know the entire probability distribution, and you don't need any information about that. So that is the intuition behind this sufficient statistic. Like whatever information I have, with that I'm okay, and I don't need to any more further information about theta. Whatever I have in the data, I'm using it optimal sense. So that was the thing. So what I will, yeah.
So over here, but given that two samples are giving the same statistic, how can we say we'll not have a common element between them? I mean, how will they be mutually, exclusive?
They can have a common element. I'm not saying. So the point I'm trying to make here, they can have a common element. I'm not saying they cannot have, but it's like a partition. You're partitioning the entire sample space in such a way that you don't need any additional information about theta. And you're partitioning it in such a way that you know this particular distribution.
Oh, okay. Yes, got it.
That is what the point that I'm trying to make here. Okay.
Yes.
So one thing you must remember, that x equal to x given tx equal to t. So tx equal to tx tilde. This will be same as probability y equal to x given tx equal to t small x. So one from the experimenter 1's point of view, another from the experimenter 2's point of view. Now, if I start from here, that theta equal to x equal to x, then p of theta x equal to small x, and tx tilde equal to t of small x tilde. Probability, I can write it as x equal to small x given tx equal to t of small x times p of theta of tx equal to t of small x. Now this is same as this guy, so I will replace this with the him. So basically I can write it in this way: tx tilde equal to t of x small x tilde p theta of tx equal to t small x tilde. So the same way you can end up writing p theta of y equal to small x and tx equal to t of x tilde, and then hence you can write the same argument p theta y equal to x. So basically x and y, even if they're seeing the same different observations, they have the same distribution. So that is under the, if they're using the same statistic, and that statistic is containing the intent information. So now if that is so, then what we can do, we can just focus on this conditional distribution. This particular conditional distribution. So the conditional distribution is p theta x equal to small x given t x tilde equal to t small x. This, it is like probability of A given B. You can write it as simple definition of probability of A and B divided by probability of B. So this is x equal to small x and tx equal to t of small x divided by probability of tx equal to t small x. Now this is same as like this first step. So I can write it as p theta of x equal to small x, and this is p theta tx tilde is equal to t small x tilde. So the entire thing can be sort of a write it as p x given theta divided by, this is a distribution of q tx given theta. Okay. So this is this is the joint PMF of x tilde, and this is the PMF of tx tilde. The idea is essentially that this px given theta divided by u of tx given theta, this will be phi of theta. If that happens, then you can say that Tx is sufficient. So this is Fisher's original approach to prove that sufficiency. So what I will do, how much time? We have 10 minutes, so I think we can quickly do this thing and then we can go for lunch. I'll do just one example and then we will move on. Okay. So the example that the most popular example is that x1, x2, xn, they are IID random samples from Bernoulli theta. So theta lies between 0 and 1. So basically xi equal to 1 with probability theta and 0 with probability 1 minus theta. So this is the definition of xi. Then f of small xi is equal to theta I to the power xi. Sorry, not theta I, theta times 1 minus theta times 1 minus x. Now if you put x equal to 1 here, then you will left with theta, because if you put it 1 here, then it's a 0, then it won't become 1. And if you put a 0 here, then you left with 1 minus theta. So this is the definition of Bernoulli distribution. Then what is the joint? Then question is, then check if Tx tilde equal to summation xi to 1 to n is sufficient statistic. Okay, so how we do that? We do that in this way. So first you figure out what is the joint PMF of x's. So the px tilde given theta is simply product of, because I have the IIT thing, so I can write it as a product of independence basically coming in, I equal to 1 to n, f of xi theta. So product of I equal to 1 to n, theta to the power xi 1 minus theta to the power 1 minus xi. Okay, and then what is the PMF of T? Can anybody tell me? PMF of T. What will be the PMF of T?
The binomial of PMF.
Yes. So the T will be following. It's a standard result n comma theta. I'm using that result. You can show it. So QT will be, sorry, I don't want to mess with the notation, so that's why. Qt given theta is basically n choose t theta to the power t 1 minus theta to the power n minus t. So now I will take this two ratios, px tilde given theta divided by q t given theta. So the product of theta to the power xi times 1 minus theta to the power 1 minus xi equals to 1 to n into t theta to the power t 1 minus theta to the power n minus t. Now I can write the numerator as theta to the power sum of xi's and 1 minus theta to the power sum of 1 minus xi's divided by n choose t theta to the power t 1 minus theta to the power n minus t. Now that means I can write it as theta to the power t and 1 minus, this is 1 minus theta to the power n minus t. Here it is n choose t theta to the power t 1 minus theta to the power n minus t. So clearly these things cancels. So I left with 1 by n choose t. Now clearly this is free of theta, free of theta. So we can say that t is sufficient statistic for theta. Okay. I'm leaving this example as assignment. You guys try. It's same way you can show it also for the Poisson. x1, x2, dot dot dot, xn follow IID Poisson lambda. Show t equal to summation xi is sufficient stat using Fisher's definition, not Fisher's information. Using Fisher information, we already have shown that T is sufficient statistic. But what I'm trying to say that you figure out what is the joint PMF of Poisson, then you figure out, you already know that PMF of T for Poisson will be Poisson n lambda. So you put the numerator point, the PMF of Poisson n lambda, and then it will cancels out each other, and you will see that something will left out where which will be only function of n and t, only data, and lambda will not be involved in it. And then that's how you can show also that t is a sufficient statistic. So this is page, whatever I just discussed today is page after this part is page 272, 73, 74 of Castle-Berger. Page 272 to 274 Castle-Berger. Okay. So next we will continue on this. Maybe another 1 or 2 discussion is required. We will do some problems also to make things more clear, and then we will next move to the next topic. Okay. All right. Anybody have any question, comments? Okay. All right. Thank you all. Thank you very much. So take care. Bye. Have a nice weekend.